Hi guys, so this video is just to go over the substitution for K that we've learned when we're working with a reaction mechanism. So what I've got on the screen right now is a reaction mechanism. It's just one that I've taken from an AP problem. It's from 1996. So this is a reaction mechanism that they've provided for us. And remember that they often tell us what the slow step is and what the fast steps are. One thing you should know is that I've never seen a reaction where the equilibrium step, and we recognize that this first step is the equilibrium step because of the double arrow, the forward and the reverse arrow. So that's the equilibrium step. I have never seen an example where that is the slow step. In my experience, the equilibrium will always be considered a fast step. So if ever you're trying to determine the rate determining step, I think it's safe to assume it is not the equilibrium step. Okay, but in this mechanism, they have told me what's fast, and I see that that middle step there is the slow step. First, remember, we can always get the overall reaction for a mechanism, and we would do this by canceling out intermediates and combining like terms. So I'm writing all of the reactants down, minus the ones that show up on both sides. So you can see N2O2 is an intermediate, and N2O is an intermediate. Remember, intermediates are things that are created and then used up in the mechanism. So my overall reaction, I have two NOs and two H2s to produce 1 N2 plus 2 H2O. So that's going to go ahead and be my overall reaction, okay? Now, most likely, if I was trying to prove that this is a mechanism, I would have already been given the overall reaction, and one part of proving that this mechanism works would be to show that, hey, the overall reaction you provided me with at the start of the problem matches this overall reaction that comes produced from the mechanism. If the overall reaction of the mechanism does not match the desired overall reaction, then it is not the correct mechanism. Okay, so that's my overall reaction. Now, for the rate law, remember that when we are working, with the mechanism, we write the rate law based on the molecularity, which means based on the stoichiometry. So we look at the slow step. In this case, that's this step right here. And I write rate equals K, just like always. And then I include both reactants or all reactants, concentration of N2O2 to the first power, because there's a coefficient of 1 on N2O2, times concentration of H2 to the power of 1, because the coefficient of H2 is 1. This is my rate law for the slow step, okay? And this rate law should match my most likely previously determined rate law. Now, there are a couple things going on that I want to mention. Number one is if there were a 2 here, then I would have written N2O2 squared, okay? But there isn't, so I didn't. But it is important to know that you would use that coefficient in that way. Let me just erase those so that it doesn't confuse us. Okay, cool. So remember that when I say you write the rate law by molecularity, it means that you actually use the stoichiometry of the reaction. Okay, the second thing that's going on here is that this rate law that we wrote includes an intermediate, and our rate law should not include an intermediate. If it does, then it is not the correct rate law. Now, we can't just rule out this whole mechanism because it includes an intermediate. Before we do that, we have to check if we have an equilibrium step in this mechanism. So if this was my rate law right here, and there was no intermediate, if this was my rate law and there was no equilibrium step in my mechanism, so that would look like this. Let's say this reaction didn't have this equilibrium step, okay? If it just had a single arrow if that was the situation where I got this rate law and I didn't have an equilibrium step in my mechanism, then this would just not be a good mechanism. This would not be a correct mechanism because this rate law involves an intermediate and the intermediate is not part of my overall reaction. Therefore, this cannot be the rate law for this reaction. However, if you have an intermediate in a rate law and you have an equilibrium step, which we do, we can try a substitution, okay? To try a substitution, what we're going to do is we're going to go ahead and write the equilibrium constant for the equilibrium step. So remember that the equilibrium constant comes from this type of situation. We've done it before in our last 2 units, where we say if I have this generic equation, my equilibrium constant, capital K, is the concentration of reactants, concentration of products over concentration of reactants. So again, concentration of products over concentration of reactants. And the coefficients are represented by the lowercase letters, and those would go up as exponents here. So if I'm going to this equation, NO plus NO in equilibrium with N2O2, I'm going to go ahead and write an equilibrium expression. K is equal to the concentration of N2O2 over the concentration of NO squared. Again, I did products over reactants, and the exponents come from the coefficients. Now you might be thinking, wait, there are no coefficients here, but actually NO plus NO is 2NO. So really this would be the same as writing 2NO, right? Like this, 2NO. And so that would be NO squared. That's where I got that from. Okay, so this is K equals N2O2 over NO squared. Now, I know that the holdup in my rate law was this intermediate, N2O2. That's what I'm trying to get rid of. So what I'm going to do is I'm going to take this equilibrium expression right here, and I'm going to rearrange it to solve for N2O2. So I can say, hey, algebraically, I'm manipulating this. The concentration of N2O2 is the equilibrium constant times NO squared. Okay. Now I'm going to go ahead and rewrite this rate law right here. Ooh, I don't know why that happened. Let me just add that back in, rate law. This rate law right here, I'm going to rewrite it, except instead of writing N2O2, I'm going to plug in this, substituting in for the intermediate. So I'm going to write rate equals K, and then my N2O2 equals K NO squared, and then I leave that H2 that I had. Okay, now this rate law looks funny because I have 2 K's. This is supposed to be a lowercase k, this is supposed to be a capital K. Everything looks crazy. Turns out it doesn't matter. We are allowed to combine those 2 K's. Sometimes the book writes it as K prime. It's okay if you do, it's okay if you don't. NO squared H2. For the theoretical understanding on why we can combine our K's, you can read the section in the book, but I think it's beyond the scope of our course and we don't necessarily have to have that theoretical understanding at this time. What we need to know is, hey, if I have 2 K's next to each other, I can combine them, and ultimately my rate law for this reaction is K concentration of NO squared H2. Notice now my rate law only includes reactants from my overall reaction. It no longer includes an intermediate. You cannot write a rate law that has an intermediate and leave it there. If you write a rate law and it has an intermediate, you must do a substitution using the equilibrium constant. If you cannot, then that would be one way to rule out this mechanism as a possibility for the reaction we're talking about. Okay, so just to recap again, when we have a mechanism, we add it up to get the overall reaction. When we have a mechanism, we use the identified slow step to write the rate law based on molecularity. That's what we did right here, based on molecularity. Once we have that rate law, we check if it matches our expected rate law. If it does not, and it includes an intermediate, we can try to do an equilibrium substitution where we write the equilibrium expression, products over reactants. We solve, for the intermediate, which is what I did right here, solved for the intermediate algebraically. And then we plug in that algebra expression for the intermediate in the rate law, which is what I was doing down here. And we're able to combine the K's into one K. And this is our overall reaction. You can write this K as regular K, lowercase, or K prime. Okay, hope this helps. Let me know if you have questions.